I'm saying hello to everyone in class. Feel free to interact freely without looking at me. I will be leaving the room.
Okay. All right. So this is going to be a little bit more of an interactive class period, hopefully. A lot of back and forth and me answering some questions, but also providing some of the initial groundwork for, one, calculating absorption spectra in VASP, and then secondly, we'll go through and discuss how the electronic structure optimization fits into geometric structure optimization, which you guys have already covered. So does that sound good with everyone? Got a thumbs up from Brendan? Okay. So from the slides Dr. Killen sent me, it looks like you guys were discussing the Conchon algorithm in the last class period and looking at how the electron density correlates to the total energy of some given molecular system. And from where that fits in, you guys are on 21 out of 30, so getting close to being finished. Yay for that. And you guys are also doing presentations in a couple lectures. Yeah, you are? Okay.
There was a centralized email to everyone with names telling who presents what. Please send me an email if you do not have idea what you are presenting.
Okay. All right. So yeah, I guess keep that in mind for a couple weeks. And if you guys have questions on any of the topics that you're presenting on, we can talk about that towards the end of class today as well. So just feel free to ask either today or just shoot me an email if you have questions. Okay. Well then, I guess the first thing that we'll jump into is calculation of absorption spectrum of a given system. And so to begin with where the spectrum comes from, we take a look at what parts are all involved in calculating an absorption coefficient. So here we're looking mainly at this Dij, the transition dipole element, for a given transition between two specified electronic orbitals. And so you guys had looked at the generation of the Conchon orbitals in terms of total energy. But one of the important things to take into consideration about dipoles is the basic idea it can absorb a photon coming in and allow for this electronic transition to happen from an occupied orbital to an unoccupied orbital. So given that if the transition dipole is not equal to zero, there's some probability of a transition occurring between those two electronic states. But the second condition needed for this is also that the energy difference between the two electronic states must be more or less equivalent to the energy of the photon, this h nu, that's going to be hitting the material. And so, I got to click up here. Okay. And so, the first thing, once you finish some type of optimization calculation in VASP, is to build what we call a file that's named OS strength. So the oscillator strength itself, if you look on the middle of the right-hand side of the slide, there's an FIJ term. So that's the oscillator strength, and it's relative to the square of the transition dipole moment for a given set of two electronic states, and then a number of constants that also go along with it. And so this oscillator strength file that we're generating is going to have a number of different components listed in it. The first things that will be listed are the initial orbital indice I. The second column will be the final orbital indice J. And then it's sorted by the third column, which will be oscillator strength. And so the way that the script will put this out is in terms of that oscillator strength, so that the highest, most probable transitions are listed first. And then you'll see the energy of transition, or the orbital energy difference, in the next column. And then followed by the directional axis coordinates of x, y, and z for the transition. And so once we have this file generated, it can then be plugged into the equation, which is done by a spectrum script, and produces the absorption spectrum. So that's kind of a brief overview on where and why the absorption spectrum can be produced. Do you guys have any questions on this so far, or is this? Okay. I don't see anybody waving hands above their head, so I'm going to assume we'll keep going. Okay. So, what is it that we need in order to calculate the oscillator strengths for a given system? So, sorry, my phone keeps buzzing. It's getting annoying. So, we do some type of optimization of the system, and it produces some type of converged wave function. So we now have solved for the Kohn-Sham orbital localization and the energies associated with each of those. And so generally in the outcome file that's generated, down towards the bottom in the last iteration, there will be a listing of the number of orbitals, their corresponding energies, and then the populations of each one of those orbitals. And so what we can try to do is we take that specific set of data of the orbital numbers, energies, and populations, and we put that into this file that we call states. So on the screen, let's see, 1, 2, 3, maybe 4 lines down in the middle, there's a set of commands that say CP states energy pop, and so that states file is the one that contains the information of what I just mentioned. And so we take that states file, which if you guys have done density of states, then that's the file you use to generate that, but you copy it into a file named energy pop, and then the other file that you're going to need is this input overlap. And it's just a new file that you create using whatever your favorite editing command is. I use VI. And we open up a new file, and it contains 3 lines. The first line will be the first orbital within the orbital range that you're interested in. The second orbital will be the final state that you're interested in. And then the third line just contains the number 1. And it's actually not used in calculating the absorption spectra, but this input overlap file is used later if you start moving towards coupling calculations, and then it's just it's a necessary value. So the main 2 input files are this energy pop and the input overlap, providing the states and their energies and the populations, and then just another file just indicating which orbital numbers to look at. Now, one thing I found in doing this is you generally don't need I mean, you generally don't need all of the states within a given system, because when you're working with systems that have thousands of electronic states, that's way too much. It's going to take forever. Ideally, you keep it less than 300 states. And I mean, if you're using a small system, only has a couple hundred, not a big deal. Then you just go one through, say, if there's 200, 200. Otherwise, you kind of break it up into regions of where the transitions might be of most interest. So anything, maybe 3 eV below the HOMO, and then go 3 eV above the LUMO, that type of transition range is generally what we're most interested in semiconductor research. And so I'm not exactly sure the whole preparing orbitals 40 and HOMO 32. There will be a series of questions when you use, let me take a step back. So once you have those 2 input files created, there's a code that he has shown here, this pathway bin OS dipole version 3. So you can execute that, and it should sit and spin for a little bit. Oh, never mind. I'm just going to go to the next slide. There we go. This one's a little bit more easier it's a little bit easier to understand. Okay. So this OS dipole script, and the end goal of this is to have it generate the OS strength file. And so you'll see a few lines pop up onto the screen after you execute, and it might sit and work for a while, and eventually we'll come up and saying mission complete, OS strength file created. And so where am I at on here? And so then we're interested in trying to look at which states are involved. Yes. Thank you for trying to call me. All of a sudden, I looked at my screen, and everybody had just started standing really still, and I wasn't sure if that was my fault. Apparently it was. Okay, let me load in these files again. So where did I cut out? Is this kind of where we got to? Okay. Is this somewhat interesting or not really? Unnecessary? I can't hear you. Okay, I still can't hear you. You guys kind of cut in and out. Okay, so All right, so we'll just, are there any questions on OS strength file generation? No? Okay, fair enough. So, also, how long does this class go? Goes until 105? 2? It goes until 2. 150? Are you sending me an email? Okay. Okay. Well, anyways. So once we have this ranking of oscillator strength files for all possible transitions across the bandgap, the next thing we want to do is we actually want to convert that into a file with the absorption spectrum information. So there's another code located in the bin called spectrum _imp, and then there's a value. I think, here he has imp1. There are a couple different versions of it in the bin, so you can use whatever works for you. There are some variations for generating spin polarized calculations and whatnot, but you can find one that works for you. And so after you prompt that command to run a script, there are going to be a number of values that the script asks you for. So the first one it's going to ask for is how many transitions do you have? And that's basically the length of the OS strength file. And so it'll give you that prompt of, if you just do word count OS strength or WCS strength, it'll give you the line numbers. Put that in. And then second thing it's going to ask for is what's the energy range that you're interested in. So are you interested in transition energies from, say maybe 2 to 4 electron volts, or a wide range of 0.5 to maybe 7. So we'll give those two inputs in sequential answers, and then it's also going to ask for some type of broadening, and the width of each line we generally put in is 0.01 electron volts, and then it's also going to ask for what is the HOMO in the system. And then you can pull that from one of your other files, and then it should execute and write out this file called spectrum. And so once you have that, it gives you a list of the energies in the system that it's sampled, followed by the second column of what is the total absorption for that given energy. So depending on what energy, transition energy range you give, is going to dictate how big the file is going to be. Okay. And so now these slides are different than what he sent me the other day. Okay, so now this is basically just screenshots of everything we just went through. In generating the transition dipole, the command is there, the bin OS dipole version 3. And then by running the spectrum file, spectrum code, and answering the questions, you produce more or less like vertical line absorption values, but then that are broadened into an absorption spectra. And let's see, I think these two slides are identical. Yes, they are. Oh, never mind, I just have two on here. So anyways, so the resulting spectrum file can be converted into a usable image, either in Excel or, we have scripts in NuPlot to do all this, or you can export it into your favorite data imaging software. It doesn't really matter. Once you guys, have you guys done any dynamics yet, or is that coming up? Not yet? Okay. So then I think that's probably one of the next few things. But once you get into looking at dynamics, you can actually start doing like time-dependent absorption stuff with the atomic coordinates of each time step, and then just finding the absorption spectra at each of those. So the images generated on the screen are using the plot software, and I mean we can modify these quite a bit, but that's generally what we use. Okay, are there any questions on generation of absorption spectrum, or we just want to get done with class relatively soon, go to lunch early? Okay. All right, so does this look familiar from your last lecture? More or less looking at the Kohn-Sham theorem. Okay. So when I'll go to the screen, it's cleaner. Right. So when we're considering the atomic positions of these nuclei and how they're arranged, each one of them comes with a different number of electrons and initial electronic structure given its location on the periodic table. And so this can also be affected by interatomic distances between different types of atoms forming bonds and that type of thing. So you're going to get this density distribution of the electrons, which then is used in the total energy of the system. And so I'm not going to necessarily rehash all of this, but this idea that we can take the locations of the electrons and use it in easier method to try and calculate the total energy is something that's very valuable. Okay. So one of the ways that Dr. Cohen, at least this is what I learned from him when I took computational courses. He used lots of flowcharts, and so given here are the way that he has his flowcharts outlined. I'm not going to sit and go through that, but if you guys are curious later on looking at it, you can have that. Okay, so you guys looked at the Kohn-Sham algorithm last time, and now how does it fit into something that you guys looked at in, I don't know, it's probably been within the first month or two of geometry optimization. So this idea that electronic structure is primarily based on three things. So in the input box up top, the very top left one, we have Ri, which is, this one's clear. All right, we have the positions of ions initially. So, and you can do this at any given time step, but we're looking at frozen geometric coordinates of atomic nuclei, and then the total number of electrons in a given system. And then the third thing we need is this convergence limit. So how long are we going to run this this algorithm? Are we just going to let it spin into eternity, or is there something that we say, okay, this is reasonable, it's good enough for now? So using those three criteria, given the position of the ions and the number of electrons, some initial density is kind of guessed. And so that's when it says density, though, it's just an initial guess of the density because we don't always know the exact geometry or optimal geometry for a given system. We're just kind of guessing relative positions. And so with this initial density, it can be put into this Kohn-Sham algorithm that you guys went through, right? So we look at the potential and how the total energy, which is dependent on density, changes. with respect to density itself. And these potentials, so these potentials are used in the one electron equations, or the eigenvalue equations shown in the second box. So looking at the kinetic and potential portions acting on some Kohn-Sham orbital produces its energy. And the total overall density is a summation of the wave function probabilities for all states. Sorry, this is getting really annoying. I haven't had this many phone calls in the span of like 5 minutes, probably in like 4 weeks. Okay, so we're looking at the total density as a summation of all electron probability, right? So the summation of each individual Kohn-Sham orbital. And so when we're looking at what he has labeled here, theta I, this initial probability is what's going to correlate to some type of partial charge density, right? You think of probability as just the square of the wave function. And so through this cycle, we get to some type of criteria where from our initial guess of the density, we produced an energy, but now through this iteration, we look at a new energy that gets calculated. And if the difference, and the absolute value of the difference between the old and the new, the 2 time steps, is below some given tolerance level, we can move on to the next step. And it produces the output of saying, here, this is what we were looking for. We've reached the minimal energy given by the parameters. Now, if that's not the case, what's going to happen is we're going to get a shift in the ionic coordinates, and then the density will shift accordingly, and then it'll go back through that same cycle in calculating the total energy on the new localized density. And so it'll sit and spin in the box depending on what the input values are for the calculation. And the end goal is just to get an optimization of this electronic structure we will get through this. Okay. When did I cut out? Back one? Seriously? That's what I cut. This one. I'm gonna stop here. Okay. Shoot. Okay. Well, I don't know where I stopped. Do you guys have any initial questions on what this means or how this gets implemented in VASP? You have no questions? Do you understand what it means? Kind of. Okay. So I guess if you're ever going to look into the outcar file, you're going to, or even if you open up the OZCAR file, you're going to see that there's a number of iterations and then printouts of total energy at some given time step. And so different steps require a different number of calculation steps in between them, given how far off of the convergence criteria they are, or how far off the geometry might be. So we could have, if we did like a one-step self-convergence calculation, like an SCF, that might take 20, 30 steps, or it might take 6 or 7 recalculations of the electronic structure itself without changing the positions of the nuclei. But if we do some type of geometry optimization, you'll see an initial energy. It might run for 10, 15 steps. You'll see an energy. It might run, it might be another 8, 9 lines before the second iteration, and so on. And you do this electronic calculation, trying to converge the energy. And once you hit your limit, okay, you move to, I guess what this flowchart is showing. So here, where he has this U equals UR circled, kind of down on the bottom, right? So this whole idea of what's the potential in looking at the energy of the system. So instead of just doing this basic concept of saying, hey, something happens here, now you can plug in this Cone-Chan algorithm into the geometry optimization algorithm. So you go from some energy, positions are gonna change dependent on what the potential is, and then you get a calculation of new atomic coordinates, and those new atomic coordinates will jump back into this algorithm. You'll solve for an electronic structure, and when that's done, it'll go back into here and continue in this cycle until either we've reached the maximum number of steps you provided in the INCAR file, or we've reached the convergence for the calculation. And so the whole goal of doing this type of electronic structure calculations to get the best energy possible, the most accurate energy possible, and also in the same way for geometry optimization, applying a little bit more intense electronic structure calculation to guide the directionality of the atomic coordinates along the potential. And so when we can get some type of optimized geometry, we might be able to find that now we're in a good spot to start analyzing the ground state electronic structure of the system and take the results like the density states and the absorption spectra as valid information from that system. And so this is more or less the same thing of the geometry optimization algorithm with this black box of not knowing what it is. We put DFT in there and calculating electronic structure to get out the optimized electronic structure and geometric structure. And so I guess these next few slides kind of just reiterate that in a little bit larger fashion, where you take this potential at the next time step equal to potential with changing coordinates, and then now you have your DFT algorithm in there, like we had. So that's kind of, that's more or less what the implementation of DFT into a geometry optimization looks like. So there's more or less two things where one is the overall goal is to refine the geometric structure of the system, but in doing so, you need to optimize the electronic structure at each one of those coordinate positions to try and guide the coordinates to the lowest energy, to try and find the bottom of that potential. And so at this point, do you guys have questions on any of this? Or are you guys running into problems and trying to calculate certain things in VASP? Or just do you have general life questions that maybe I can answer? We can have a fireside chat with John. Not really? You're cutting in and out. So your email, sorry, I just saw your email, was asking about if the dipole reads the wave car. Yes. Are there any other questions? Oh, I guess there's one more slide. So, would you agree that this is what you achieved today? Did you achieve an understanding of how this code works? An ability to operate the codes efficiently? Or understanding possible errors that may arise? Yeah? Okay. Anyways, so, well, if you guys understand this, great. It took me longer than one class period to get this all figured out. But now that you have an ability to calculate an optimized structure, the next thing you guys are going to start to do is to start running heating calculations and molecular dynamics. And the ability to understand how forces are interacting between different ions, different atoms, allows for the study of things like that I do, nonlinear dynamics, or chemical reaction types of just looking at different ways that the atoms are interacting. And so depending on what type of functional you use within DFT calculation will give you different results just based on if it's a pure functional or a hybrid, so like what percentage of hydrogen is used, but also the different exchange correlation pieces that are used between different functionals. And I guess you guys are going to have, maybe that was when I took the course. I don't know if you guys are going to have an actual developer of functionals talk or not, but that can also be fairly interesting. And so, yeah, that's more or less what I got. And I'm happy to sit and answer questions for you guys. Otherwise, you guys get to do what you want. Live your life.
It is. Oh yeah.
Okay. Good deal. All right. See you guys. Have a good rest of your day. Oh, and Aaron, I'll send you an email later this afternoon. I have an email. All right.